All right. So my name is Jack Wadden. I'm an engineering manager for Akamai Technologies. First, I just want to thank everyone from Opennebula for asking me to be here and to speak to all of you about what Akamai is doing with Opennebula. I'm going to tell you a little bit about Akamai for anyone who's not aware, then introduce the problem that we're trying to solve at Akamai with Opennebula, and then I'm going to get into some technical details about what we faced on our journey with Opennebula. Akamai is a CDN, which stands for Content Delivery Network. So we make the internet fast, reliable, and secure for our customers. We do this by operating a globally distributed network of servers that cache content close to end users in order to accelerate the delivery of content on the internet. We also support scalable live media streaming and protocol optimizations for raw IP acceleration. At the heart of Akamai's system is a DNS-based load balancing system that basically sends you to the server that's closest to you, that's most optimally positioned to serve your web requests. So Akamai operates at massive scale. We serve 15 to 30% of all internet traffic, which equates to over 3 trillion hits per day, regularly serving over 30 terabits per second of traffic. Our platform consists of over 215,000 web servers that are deployed in data centers around the world. So really, really massive scale. 120 countries we have these servers located in. And our system is very complex and very integrated. Highly complex distributed system consisting of over 1,000 software components and over 100 unique server roles. Which brings us to the problem that I'm here to tell you about today. System testing at Akamai is very challenging. In order to test Akamai systems in the lab, we need to build some semblance of a replica of this enormous distributed system that we're running on our production platform. And that's very challenging. At Akamai, we call these mini instances of Akamai's distributed system testnets. Testnets are our system test environment. They consist of all the different infrastructure systems, security systems, and user-facing systems that are serving content to all of you. But testnets at Akamai are a scarce resource. They are expensive to build and require a huge team to maintain. So we have to invest a lot in terms of hardware and subject matter expertise to stand up an instance of Akamai. And each instance of Akamai that we have has an equivalent incremental cost. So we have to manage and upgrade and maintain and do care and feeding for each one of these environments separately. We really only have about 4 semi-complete instances of Akamai's system to test on. And so with a company of over 6,000 employees and probably about 1,000 engineers, you know, 4 test instances of Akamai's distributed system. It could be the Borg from my earlier slide, maybe. So yeah, basically, you know, 4 instances of Akamai is not really enough for all of us to test on. And we're sharing those environments. We have, you know, groups testing system X on one environment while another group is testing system Y on one environment. And, you know, that's not without its problems. First of all, because we're sharing these environments, we frequently run into disruptions. So the activities of one group rolling out a bug in their software may disrupt the testing activities of another group and create confusion and delay. Sometimes the fit is poor because we've only have these 4 environments. They need to meet everyone's needs, and that means they don't meet everyone's needs perfectly. And when we can't customize them, or when we need to borrow a piece of the environment from someone else, we have to coordinate with other groups, and that leads to inevitable delay. So what would we like to have we'd like to take away some of those problems. We'd like to have a low barrier to access, make it very easy for people to get involved and start testing at Akamai. We'd like to enable no block debugging. Right now, if we hit an issue in a test environment, testing may need to stop until we can get developers to take a look and determine what's going on. And we're not making progress during that time. Portable and restorable configuration would be wonderful. And destructive testing, being able to make a mess without having to clean up that mess would be absolutely wonderful. Of course, we'd like to eliminate the coordination and sharing problems that we have. And the biggest one for me is enabling automation. If we have 4 test environments, we can't perform continuous integration testing where we're going to be constantly rolling out potentially buggy software to an environment. So having a place where we can run test automation would be an enormous thing for us. And we'd like to make the maintenance process more efficient and fix that problem of having an incremental cost for each environment, and make better use of the hardware. I think we have about 15,000 servers in our lab right now. So our vision for VTastic, the project that I'm here to tell you about today, is to offer continuous, automated, end-to-end testing for all engineers on every component at Akamai. And the way that we're doing that is with a concept that we call testnet cloning. So we've built a 5th instance of Akamai on virtual machines using Opennebula. And we've built a web system on top of Opennebula called the VTastic Resource Tracker. And VRT is able to take this collection of VMs. It has some Akamai-specific features and understands that this collection of VMs is one instance of Akamai's distributed system. We can click a button in our UI, and VTastic will ask Opennebula to shut down all of those VMs and save their disks to persistent storage. Of course, we also save off the VM parameters, and that allows test harnesses and engineers to come back and ask VRT to start a copy of that saved snapshot. And we can run multiple clones of our master testnet concurrently. So that's the VTastic concept, is to be able to modify, save, and clone snapshots of Akamai's distributed system. The master testnet is one of the major focuses of the project. We've formed a separate team just to handle management of this master testnet. It's an asset for us. And we're working with groups around the company to build out this master testnet. And so our process basically involves us cloning that master, making modifications, then saving that candidate as the new master, and then moving on to create another candidate for further changes. And while that's happening, groups who are doing testing could clone any node in that tree of masters to perform their testing, or even do customizations that would let them, that they could save and then use for themselves in their own testing. So one thing that some of you may be thinking is, if we're going to be able to clone these systems, how do we handle the identity of all these systems? Akamai machines do not use DHCP. We assign static IP addresses. We have DNS entries, all sorts of on-machine state that has the IPs of the machines. In effect, our platform, our servers know each other by their IPs. So we can't change those IPs when we make a clone of our systems. And our solution to that problem is to use private IP space. So we're using Opennebula to allocate VLANs in our lab for each testnet clone, and running each testnet clone in its own isolated Ethernet space behind a NAT gateway, behind a NAT gateway. And so this lets us run multiple identical clones on the same hardware in the lab. And we've developed a set of tooling that allows us to tunnel through that NAT gateway to get into the IP space of our clones. The first tool is called vPoint. vPoint will start a bash shell that's configured with an open source component called Dante. Dante is an LD preload that essentially wraps itself around every application we execute from within that shell, and it intercepts IP communications or hostname lookups and attempts to transparently tunnel them through the SOX proxy. So I can run this vPoint script to attach my shell to a specific testnet And then I'm able to SSH, SCP, run Akamai's deployment tools, and just generally interact with that particular clone and its /16 of IP space as though it were reachable from my machine, even though there's actually about 50 instances of that private IP space running out in the lab. We also have tools called Chrome vPoint and Firefox vPoint, and they start dedicated browser sessions that have a custom socks configuration so that we can interact with web applications and pull content off of our test instances. So our design approach is to build a set of centrally managed infrastructure. The VTastic team is managing and supporting this system on behalf of the entire company, and do that on commodity hardware with open source technology. Because we are operating so many servers around the world, we've got a lot of leverage for purchasing hardware, and so we've started the project just by using the best server profile that we could find that was already available within Akamai. And so some details about that. We operate the VMs on dedicated servers, and we store our VM disk images on separate servers. So the VM hosts are 32 core machines with 128 gigs of RAM. They each have two 10 gig Ethernet cards. We use the front-end card for administering the VM hosts and for disk I/O to storage. And we use the second Ethernet card for all the inter-VM connectivity. So basically our test nets, our VNets are connected to the back-end NIC, and all of our storage communication goes over the front-end NIC. The storage nodes are 8 core machines, 32 gigs of RAM. We RAID all of the drives together, SSD drives, and our current production cluster has about 40 terabytes of storage space. So this gives us enough capacity to run approximately 40 to 50 Akamai testnets concurrently. We're able to start subsets of that testnet if you only need part of Akamai for your testing. So the testnets consist of between 30 and 120 nodes each. And in total, we can run about 1,500 to 2,000 VMs on our current build-out. Our master testnet is 120 nodes, and after we've sparsified all of the images and flattened them, it's about 1.5 terabytes in size. We expect that to grow to something on the order of 500 to 600 nodes in the next 2 years. So now I'm going to go through some of the evolution of our project. When we started with Opennebula and the VTastic project, we've been using GlusterFS. And when we started, we were using GlusterFS with its fuse mount. QCOW2 backing files and child images stored remotely on that Gluster system. The static snapshot images and the running VM scratch disks were all on remote storage. And we had issues there. We saw memory leaks in the fuse mount and occasional hangs in the fuse mount, which would cause us to lose VMs. And at that point, when we would lose a VM, we could just start the VM back up again, and it was generally recoverable, but it wasn't a great place to be in. So then we started to work on Gluster Direct feature, using Gluster's libgf API that Opennebula can configure. And we were still keeping the backing files and the scratch images on the remote storage, and Gluster uses the fuse mount Opennebula uses the fuse mount for image management. So in this configuration, things were really not better. In fact, they were quite a bit worse. We were losing testnets frequently, or parts of testnets frequently, and when we lost them, it was catastrophic. So the VMs were not recoverable. At that point, we went back to the fuse mount, and we started putting the VM's running disks, their scratch images, on local storage. So now, QEMU is opening a disk image that's on the VM host's local disk, and that disk image's backing reference points to our Gluster mount. So the snapshot images were on remote storage, and the running VMs were using local storage. This meant that snapshots took a little longer because we would have to copy those images out to our storage system when we wanted to save a snapshot. It also closed the door on live migration. We'd really like to be able to move VMs around when we notice that hardware is failing, and this approach would not support that. We did still experience some occasional fuse mount problems when cloning VMs or saving VMs. And generally we just don't trust Gluster at this point. It's actually been working great for the last 8 months. VTastic has really gotten off the ground. We've got engagement from around the company working to build out that master testnet, and we've had almost no problems over the last 6 months. But when we first switched to this architecture, we were still seeing the same sorts of problems that we had seen in prior iterations. We got a new set of hardware and moved to that new hardware, which involved standing up a new Gluster volume, and at that point our problems went away. So we think that perhaps there was some corruption in the state of the Gluster volume we were running on, but that just doesn't leave us with a warm, fuzzy feeling. And so what we've been working on now is integrating with Seth. So that obviously means that we'll have our static images and our running VM images on remote storage, which opens the door again for live migration. We think that this may be the holy grail, but in English we have a phrase, the devil you know versus the devil you don't. And so that remains to be seen. I anticipate that within the next couple weeks we'll begin some scale testing of Opennebula and VTastic on Ceph. Well, one feature that we'll need to add in order to do this is to be able to create trees of RBD clones. Today, the Ceph driver, when I create a VM based on a non-persistent image, it's created as an RBD clone child of that image. But when I save it back to the data store, it gets copied and created as a standalone flattened volume. And so we'd like to be able to build longer trees of images as we're revising. And so we're going to work on that feature this week. And some future possibilities that we hope to implement as VTastic succeeds are the ability to incorporate physical hardware into our testnets. So we think this may involve a move from VLANs to VXLAN, which would also remove our cap on VLAN ID availability in the lab. VLAN IDs in our lab are a limited resource. So moving to VXLAN will give us essentially unlimited VLAN space. It might allow us to develop a feature whereby engineers could incorporate physical hardware into the testnet environment in order to drive load and performance testing against the physical hardware and have it be supported by a set of cloned, up-to-date functional infrastructure. Adding realistic network conditions is interesting for a number of groups, and possibly running virtual routers or doing some sort of SDN so that we could actually create subnets and do internetworking within the environment. Our mapping system is monitoring the internet. Our load balancing system, I should say, is monitoring the internet closely, and that's not very realistic when you're testing on a /16 LAN. So that's what I have. Are there any questions?
Hi. You were talking about IPv4 addresses, and you have a NAT gateway. So how do you deal with static IPv6 addresses?
We're not going to be able to traverse the router, I think. So we haven't actually set up IPv6. There's a number of groups that are using Opennebula just as small VM farms, and they've had great experience taking Opennebula, setting it up very easily on a limited set of hardware just to create VMs that they pretend are regular machines to build out their testnets as a part of our bare metal testnets. And those groups are using IPv6 with the same stack that we're using in VTastic, but we haven't actually configured it. Our services team is working on that now as well. And so as we turn that on, we think that inter-VM connectivity over IPv6 should require little to no work. But traversing the NAT gateway with IPv6, we're not sure there's going to be any value there. If we set up some sort of stateless NAT, then when you make a clone, you could find out what is the prefix, the external prefix that's been assigned to my clone. But I'm not sure anyone could leverage that in a meaningful way. And so it's likely that what we'll do is, deploy any testing software inside the environment so that it can speak IPv6 inside that isolated environment.
You mentioned the number of nodes you're using and also the amount of storage in terabytes. Is there any requirement or bottleneck in the I/O or latency? What are you looking at there?
Not yet. And when we started this as sort of a proof of concept, right, we scrabbled together the strong hardware that we have available for production and chose these server profiles because they were already available to us. And we had a small Akamai testnet, just our core infrastructure, and we said, this is not representative of the sort of disk or network I/O that we're going to see as the testnet environment grows and starts to be used for more and more realistic testing. And so we said, we're not going to think about that stuff right now. Let's focus on building the web system, getting these pieces integrated, getting a system that's running, and getting groups to engage and start building out the master testnet. And so really the most I can say on that topic is that it hasn't been a problem. Our NICs are far from overloaded. The disks on our storage systems are far from overloaded. There's no RAM or CPU problems on those servers. So as it's grown and people have started to use it for real testing, we've had more nodes in the testnet with sort of ambient load. We're not seeing anything concerning in terms of the I/O profile. And my hope is that we'll get to the point that we'll start to look closer at that aspect and think about what we can do to tune the system and get more out of the hardware. And right now we're just sort of brute force using it, and that that's been a good choice because we have seen that the profile has changed as the testnet's grown and as people have started to use it. And I don't think that that's leveled off yet. I don't think that we could characterize what the requirements of the system are fully at this point.
You're still at the MVP phase, like warning about the system.
Yeah.
No more questions? Okay. Well, thank you very much.
Great. Yeah. Thank you guys.
We're going to take a break.